Okay.
So good afternoon, everyone. Welcome to session 5 of ICNP 2020, Controlling Traffic session. I'm Chathu Ranaweera. I'm from Deakin University, Australia, and I'll be the one who's moderating this session today. So in this session, we have 3 presentations. Before we invite the speakers to present their papers, let me quickly go through a couple of housekeeping rules we have. Please keep your microphone and camera off during the presentation, of course, except the presenters. You can also ask questions at the end of the presentation. You can switch on your microphone and camera when you're asking a question, and you can also ask questions via the session Q&A tab of the Who app. And the presenter will answer those questions at the end of the talk. I'll ask those questions. I'll repeat those questions for the presenters. All right, let's get things started by welcoming our first presenter, Balajee Vamanan, who is an assistant professor of computer science at University of Illinois in USA. Today, he's going to present their paper titled to Legilimens and Agile Transport for Background Traffic in Cellular Networks. Balajee, are you ready?
Yes, I am. Okay.
Right.
Thanks so much, Chatrika. Welcome, everyone. Good morning. Rather, I should say good afternoon. The title of my talk is Legilimens, an Agile Transport for Background Traffic in Cellular Networks. This is a joint work between UIC and AT&T Research. Most of the heavy lifting has been done by the students, but unfortunately, the students have graduated. So I'm giving the talk today. So let's get started. Over the last several years, cellular networks are increasingly used by apps such as cloud data sync and software updates. These are applications such as your iCloud, Google Drive, software updates to the phones, tablets, and so on. These apps transfer large volumes of data using the cellular network. So in the process, they degrade the performance of your regular foreground applications like web browsing, YouTube, social networking, and so on and so forth. They also, by transferring so much of data, they interfere with the neighboring cells. So this problem gets worse when these transfers use what we call as fast share protocols like Cubic or Reno. Because when you use these fast share protocols, the background data transfers will compete with the foreground traffic and share the capacity equally. So this is not a good thing. So we need mechanisms that efficiently handle the background data transfers without affecting the foreground traffic. So let's see what existing approaches do. So we can broadly categorize the existing approaches into 2 classes. There are in-network approaches and there are end-system approaches. So in the in-network approaches, we have the well-known QoS class identifiers or QCIs. This is a layer 2 mechanism. So naturally, all the application flow level information is already lost in layer 2. So this is very inflexible. Also, because it's layer 2, it has to be provisioned. The priority levels have to be provisioned by the operators well before the application can start. So this is not like really flexible. In the end system approaches, we have the low priority transport protocols like LED batch, TCP/LP, TCP/NICE. In general, these protocols are delay based. They sort of keep monitoring the delays and then they react. But because cellular networks exhibit highly varying delays, there is also per device queues in the base station, and there is an in-network scheduler, the delay is not such a good measure of congestion. So to the bottom line is that existing in-network approaches and end-system approaches do not address the problem of large volume background transfers. So that brings me to our contributions. We present Legilimens, which is a low priority transport designed exclusively for cellular downlinks. It has 3 technical contributions. The first contribution is that Legilimens includes a novel capacity and load inference algorithm. The algorithm overcomes and in fact leverages the existing proportional fair schedulers in the network. The algorithm is robust to sender and receiver side optimizations like delayed acknowledgements, batching optimizations like SRO, GRO, and so on. The second big technical contribution is the implementation is fully contained in the sender side. So there is no change needed to the cellular infrastructure. And our third contribution is that we have demonstrated our design by building a real implementation and evaluating it in a live LTE network. Our bottom line performance improvements are impressive. Our evaluations show that Legilimens improves the throughput of background flows by a factor of about 3 on average over existing low priority protocols without hurting the foreground flows. So here's the outline of my talk. I'm going to start with a little bit of quick background on how cellular networks are fundamentally different from wired or Wi-Fi networks, and also show some preliminary data on why existing low priority protocols do not do a good job. Then I will talk about some of the design insights of Legilimens. Then I'll present some interesting results. Then I'll conclude the talk. Okay, so when it comes to cellular networks versus Wi-Fi or wired networks, there are 3 key differences. The first difference is that the links exhibit varying capacity and delay. The second difference is there are per device queues in the base station. And the third difference is that there is an explicit scheduler to arbitrate among these per device queues. Proportional fair schedulers are commonly, or from our knowledge, mostly used. But the key takeaway is because of these 3 factors, delay is not a good measure of congestion in cellular networks. I want to sort of briefly talk a little bit about proportional fair schedulers because it's central to our proposal. These are commonly used by cellular operators for the downlinks. One of the major selling points of proportional fair schedulers is that they balance utilization and fairness. The high-level idea is that the scheduler allocates resource blocks to the client that maximizes the ratio of capacity to recently achieved throughput. So you can see that the clients with good signal capacity, good signal strength, get higher priority, but also for fairness, the recently achieved throughput will sort of move the clients towards sort of fairly sharing the network. So the winning client, every round, this ratio is computed, and then the winner is chosen, and the winning client gets all the resource blocks so long as there is enough data to send. So the PF schedulers provide opportunity to clients with bad signal, and also at the same time provide high throughput to clients with good signal quality. From our experience by talking to cellular operators, we find that PF scheduler is the de facto standard scheduler on mobile broadband data bearers for downlinks. So just as I mentioned, the existing LPT protocols use one-way delays to estimate congestion. But because one-way delays are not very reliable in cellular networks, we do not see them performing very well. So to show that, we did a simple experiment with just 2 flows. We have an on and off foreground flow, which uses cubic, and an always on background flow that uses TCP/LP. So we sort of run these 2 flows in both Wi-Fi and cellular networks, and we sort of see how the throughput varies over time. So these are the plots that compare the performance of one existing LPT protocol, in this case TCP/LP. So you can see in Wi-Fi, whenever the foreground flow, which is represented by the blue line, whenever the foreground flow starts, it starts around 30 and then goes off at 60, and then again starts at 90 and goes off at 120. So we clearly see a pattern. In Wi-Fi, whenever the foreground starts, the background flow, as represented by the red line, backs off. And then when the foreground finishes, the background picks up. And then this is sort of the intended nice behavior. However, if you go to the cellular network, it's all over the place, right? So from this experiment and from a series of experiments, we have concluded that the combination of these three factors, varying delays per device queues and the scheduler, means that one-way delay is not a good measure of congestion or load in the network. And that's the reason why existing low priority protocols do not perform well. Okay, now let's talk about Legilimens. So the high level idea of Legilimens is that we want to design, our design has two distinct modes of operation. There is sort of a throttled mode, which we call it as a gap mode. In this mode, we completely throttle the background transfers while probing for contention at a very low constant rate. We stay in this mode as long as the load is high. But when the load is low, we go to the normal mode where our background transfers can use any congestion control algorithm and then can send data. So a quick note about this probing mode, we call it as gap mode, which stands for gradually aggressive probing, because in this mode, we first start probing using very small bursts because large bursts impose a high overhead, and we gradually increase the burst size to get more confidence. So from this high level picture, you can see that the key requirement for our design to come together is that we need an algorithm to detect if the base station is busy, that is busyness, right? So that brings me to how to detect busyness. So to detect whether the base station is busy, we exploit this observation that the PF scheduler itself can be sort of leveraged to detect whether the base station is busy. So to expand a little bit further, because of the nature of the PF scheduler, when new foreground flows join, the scheduler by design, by construction, will give an opportunity for the new incoming flows. And when that opportunity, when the new flows get the opportunity, existing flows will observe gaps in their receiving sequence of acknowledgements. And we can observe these gaps using timestamps, and we can detect whether there is competing traffic or not. So for example, if you look at this simple figure where there are two clients and both of them are receiving from two different senders, I've only shown the sender one, which let's assume that it's been sending for some time. So when client two starts receiving data, the sender one and both the packets are destined for client one and client two, sort of they end up queuing up in the base station, and both of them get opportunity, roughly based on the heuristic of the scheduler. But the key thing to note is that when there is a competing client that's also receiving the data, there will be gaps in the timestamps of the acknowledgements, which we can observe and sort of detect if there is contention or not. So this overall works well because the cellular link is normally the bottleneck. But it's not that simple. This is only like a high-level insight. When you have delayed acknowledgements and batching and all systems optimizations, this doesn't usually work that well. So the reason is that the delayed acts and batching artificially produce gaps in the timestamps. So now the question is, how do you detect busyness when there are delayed acts and batching? So here again, we use this key idea that we have to estimate the capacity of the sender in addition to detecting the gaps in the packet reception. So then we can use a simple sort of high level heuristic that if there is no gap, we know for sure that the network is idle. But if there is a gap, but if your sender, if your receiver is already receiving at a throughput that is roughly equal to the capacity, then also we can infer that this gap is artificial due to sort of optimizations like batching and not really because of contention. So combining these two, we sort of try to mine the scheduler and try to recreate the schedule at the sender with minimal information. So this is not very simple. The actual algorithm is much more complex because we have to filter outliers, and we have to also account for the PF scheduler parameters. So I will urge anyone who is interested to go look at the paper for the complete algorithm. So one more quick note before I dive into the results. In our actual implementation, we don't use one probing mode. We use a series of 3 probing modes, which we call it as gap modes: gap mode 1, gap mode 2, and gap mode 3. The big difference at a high level is that each successive mode sends a burst which is twice as big to increase the confidence in our estimation. But at any point we infer that the network is idle, we actually sort of go back to the previous mode. Not only that, we sort of wait, the waiting interval sort of becomes exponentially larger, resembling something like your the CSMA, the random backoff that's used in CSMA. But because we have this random backoff in probing, when multiple background flows compete, this exponential random backoff also guarantees fairness. And we have the analysis of fairness in the paper. Okay. So now I want to talk about some interesting results. So we used 3 testbeds to evaluate Legilimens. We had a real implementation on a real network, and we evaluated during both idle and busy hours. We also used PhantomNet to do more controlled experiments, and we relied on simulation for scalability studies. Our actual implementation in the kernel uses the Linux's a modular congestion control framework. It's about 300 lines of code. We have to enable the TCP timestamp option. Our testbed has 6 phones, and the carriers of 10 megahertz carriers, band locked, and each experiment lasts for about 4 to 8 hours and transfers about 100 GB of data. So it's pretty exhaustive. So the first result I want to show is the proof of concept. For this, we repeat the same experiment we did with TCP/LP for Legilimens and show that it works as intended. So we have one on-off foreground flow, which uses the cubic, and one always-on background flow that uses Legilimens. And we sort of compare the average throughput versus time, and we plot it. So here, the red line shows the average background throughput, and the blue line shows the foreground throughput. The foreground starts around 30, goes off around 60, and again starts at 90 and goes off around 120. We can see that Legilimens sort of takes the full capacity when there is no background, when there is no foreground, and then when there is foreground, the background, which uses Legilimens, backs off, and then it sort of performs as intended. So that's sort of only the proof of concept. The next interesting result I want to show is how it performs in a realistic network, with a realistic workload, with the combination of different flow sizes and different load levels. So for this experiment, we sort of identified a night time where the network is quiet, and we ran an experiment with different flow sizes at different load levels. And we compared the performance of the long foreground flows and the performance of the background flows. These figures show their throughputs for different load levels and also the average. We compared a number of systems where the foreground always uses cubic, the background can use cubic, can use LED BAT, can use TCP/LP, and can use Legilimens. So we sort of compare how each of these protocols perform as a low priority protocol. And we do this for both background and foreground. So from this figure, simply focusing on the average, you can clearly see that the foreground flows achieve throughput almost close to having no background flows at all, which is great. Or sometimes they achieve closer to the existing best low priority protocol that's used for background. And if you shift the attention to the background performance, the background flows achieve much higher throughput than existing low priority protocols. We cannot compare to Cubic, which is a fair share protocol, because that severely hurts the foreground performance, which is important. So another thing we also want to show is how our approach reduces the load on the network. So for this, we ran the same experiment during the busy hours at different load levels, right? And then we compare the amount of data volume that Legilimens injects into the network as compared to Cubic. So we repeat this for varying number of load levels, and also we show how the overall physical resource block utilization PRB varies. So basically here the dark, the black shows the base load that's already there because of other users, and foreground is denoted by a dark gray, and the light gray is the background, right? So from this, we observe that Legilimens consistently consumes less data than Cubic, right? So in other words, Cubic creates the same traffic regardless of the underlying network load because it's a fair share protocol. So the net result is that Legilimens results in much lower utilization, about 14% lower. So I'm almost near, I think, my time. So to conclude, I presented Legilimens, which is a low priority transport protocol, which is optimized for cellular networks. It has low complexity, requires no change to infrastructure, and it maximizes the background throughput without affecting the foreground traffic. So Legilimens provides a way for the for all the stakeholders to achieve their end. So it balances the needs of users who want good performance for foreground apps, content providers who want good performance for background apps sent to transfer large volumes of data, and network operators who want to sort of minimize the resource utilization so the network is not overloaded. So it provides a way to achieve all of those. Note that our work only focuses on cellular downlinks. In the future, we're going to look at uplinks. So with that, I conclude my talk, and I'm more than happy to answer any questions that you may have.
Thank you, Balajee, for your interesting talk. Are there any questions out there?
Yes, I have a small question. I would like to say thanks for a really nice talk. I want to ask, what is the task for EMBMS while we have background traffic? So what is the task for EMBMS in, let's say, in the, I don't know, uplinks or downlinks? We can manage, I think, uplinks with EMBMS.
Right. So our work focuses only on downlinks, right? And we have to go back to the goal. So our goal is we wanted to design a protocol that is flexible for application developers to sort of, let's say you're writing a big software application and you're starting a number of flows, right? And you don't know beforehand which flows may need to go to the low priority and which may not, which you want.
I want to know now, I'm so sorry. I want to know, EMBMS is, doing broadcasting the background traffic. We don't need to manage.
No, but this is, so broadcast is a completely different beast altogether, right? Because many of these, for example, if you're using some cloud syncing app, you don't want broadcast, right? You because everybody is downloading a different set of data. So, I mean, broadcast may work for something like updating bulk firmwares on connected cards and things like that. but not necessarily when you're, this is more general. That's how I will look at it.
That's true, but you showed that in the second or third slide, you had the update for iOS something. This is all multicast.
Right. So you're right. So the one use case, that is the software update, you can do it with broadcast, but
Yes.
but we also cover all other applications which are not broadcast.
Yes.
I hope that clarifies. Right. So broadcast, I mean, this could work for software updates, but this could also work for.
Yes, you are right. But I want to know, could you please give me some examples which is the background traffic and we don't want to multicast it?
Oh, the classic example is, let's say any of these, your cloud sync apps, right? Like Google Drive. Let's say you want to access some files offline when you're on the move, right? And the files are being transferred from the servers down to your phone, and that will be personalized data.
Yes, because your image mixed my mind. You put the iOS update over there, and I said, "Oh, what?"
Yeah, I understand that might have been slightly misleading. Sorry about that.
Thank you so much. It was nice to hear. Really, it was nice stuff.
Thanks.
Hi, I have a question.
Yep.
So thank you very much. This is really cool technology. Let me try to understand it from the perspective of the ideal solution would be for the network to explicitly offer an option for low priority traffic. And the question then is, how good can a workaround, which hopefully it's fair to say this is, achieve the same thing? And from the way you explained it, it sounds as if the service provider's queuing is trying to eliminate any visibility to you as to what other users are doing. So the actual metric of whether or not the network is congested seems to be that at a given known receive condition, your high priority traffic gets lower throughput than the maximum throughput in the same receive situation. Is that true?
So I think the one thing I want to clarify is that you want to use Legilimens only for the lower priority background transfers. And if you do that, then anytime a high priority traffic joins, your probing will detect using a combination of different heuristics that some other competing traffic, it could even be other low priority, right? But the moment it detects a contention, it backs off. So the high priority transfers do not use Legilimens. They'll have to use whatever, cubic, Reno, or compound, or whatever. So they are not affected. Am I getting your?
I understand that. What I'm saying is that the heuristics seem to be depending on understanding certain side effects of the queuing mechanism of the service provider, which I'm worried about may or may not be always the same and continue to be always the same. So I'm trying to understand what is really the unavoidable visibility that you have as a single user with a single phone into whether or not other users are effectively taking bandwidth away from you because they have high priority traffic.
Okay, this is an excellent question. So yes, so I want to right away acknowledge that we are mining, right? Our design assumes that the mechanism that is used in the base station is proportionally per scheduler, right? And this we have from our by talking to several operators, almost all of them told us they use the PF scheduler. And if you use the PF scheduler, by design, what happens is that you can assume that anybody who joins afresh will get a turn immediately, right? And when they get a turn in the schedule, that will reflect in your receiving acknowledgement stream as a gap, and which you can mine. So you are 100% right that if the provider changes the scheduler to something completely different, Legilimens will not like our heuristics will not work well. But because it's almost universally used, that's why it will work today. Did I answer your question?
No, I got that. What I didn't get is I guess probably too long here and read the paper, but the indication, this mining that you said, when it happens when another user joins, right? So
Yeah.
what happens if I am joining? I'm in steady state. How do I know how many other users are there in terms of how do I, determine the congestion
Okay.
situation in steady state?
So I think the short answer to that is that I don't need to detect the extent of contention. I just need to detect contention. It's a binary choice. So we are detecting whether there is somebody else with whom I'll be competing in the base station. So long as the answer to that question is true, I am going to back off as a low priority sender. I don't really care how many other people I'm contending with. So long as it's more than 0, I'm going to back off. Right?
Okay.
So
Cool.
I'm happy to discuss this offline. Excellent questions. Thank
Yeah,
you.
sure. Thank you very much.
Thank you. I think it's time to move on to our next talk. So let's thank the speaker again. And if any of you have any questions, you can of course contact Balajee, or you can ask that question in session Q&A tab, so Balajee can answer your question offline.
Oh, of course. Thank you.
All right.
Thank you.
All right. Our next presenter is Bilal Tayh, who's a master's student at Ben Gurion University in Israel. Let's welcome Bilal to present their paper titled Cooperative Network Wide Flow Selection. Are you ready, Bilal?
Yeah. My name is Bilal Tayh. I'm a master student at Ben Gurion University. My name is Bilal Tayh. I'm a master student at Ben Gurion University. The paper I will be presenting today is titled Cooperative Flow Selection. Network-wide flow measurement is fundamental in applications like identifying attacks, detecting load imbalance, performing traffic engineering, and routing. Network-wide flow measurement can be achieved by measuring the size of each flow. In controller, the controller collects the measurement data from network measurement points denoted as NMPs, and they attain a bird's-eye view of the traffic within the entire network. Network-wide measurement is challenging to implement due to the rapid line rates that force network devices to use fast but scarce SRAM memory that is too small to store all the flows. And as we said earlier, network-wide flow measurement can be achieved by measuring the size of each flow. There are two types of works that solve the problem. Works that pursue some form of communication between network measurement points, and works that don't require communication between network measurement points. We will continue the works that don't require communication between measurement points, because these algorithms are simpler because they run on each network in each measurement point separately, and they don't need communication with other measurement points. We suggest cooperative flow selection algorithms that achieve near optimal flow coverage. A flow coverage is the percent of monitored flows out of all the flows in the network. In network-wide measurement, optimality is the highest coverage possibly achievable by any offline algorithm. We evaluated our algorithms and explored their benefits and limitations compared to prior works. The topology we use in our evaluation is FAT3, which is common in data centers. The FAT3 topology uses parameter k equal 8 and consistent of 80 switches and 128 hosts. In our evaluation, we assume that all switches participate as measurement points. we want the measurement points to choose flows to monitor without communicating between each other. The problem is, if a measurement point chose randomly, the same flow will be monitored in multiple switches at the expense of flows that no measurement point chose to monitor. So how we solve this problem? We use the fact that each measurement point in the path sees the packet with different time to live. So we use the time to live to break the symmetry and to make sure not all the network measurement points choose to monitor the same flow. Each network measurement point can monitor flows using monitoring entries. Each entry contains flow identifier, packet count, byte count, and grade. The network measurement point chooses to monitor the flows with the lowest grades. So when a new flow arrives at the measurement point, we compare its grade with the grade of the already monitored flow with the highest grade. If the new arrival is smaller than the grade of the flows with the highest grade, we will choose to monitor the new flow. For example, if a new flow just arrived to the measurement point, and let's say that the grade of the flows the highest grade in the measurement point is 0.6 in the first entry, and let's say that the grade of the new arrival flow is 0.3. The grade of the new arrival flow is lower than the grade of the flow with the highest grade. So the measurement point will choose to monitor the new flow at the expense of the flow in the first entry, in this case, that has the highest grade. So the measurement point will choose to monitor flows with the lower grades. Determining what grade to give each flow at each measurement point means determining what flows to select at each measurement point. And to maximize the diversity of monitored flows, we need each measurement point to select different flows, which means ideally only one measurement point selects each flow. To achieve that, we want flow to have a low grade in one measurement point and the higher grade on the others. So how does a measurement point determine a grade of a flow? We assign each flow with the hash value within the unit circle. We assign a target value for each possible time to live value. The grade of the flow in a measurement point is the distance between the hash value and the target value. In this example, we have a path. This path is a part of a network. All the measurement points entries in the path are full. Let's assume for now that the target for time to live 255 is 0. The target of 254 is 0.33, and the target of time to live 253 is 0.66. A new flow travels from its source on the left side of the path to its destination on the right side of the path. Let's say that the hash value of the flow is 0.05. So the first NMP calculates the grade of this flow, which is the distance between the hash value and the target value. Let's say that in this example, the time to live starts at 255. As we said, the target of 255 is 0, and the hash value is 0.05. So the distance between them is 0.05, which is also the grade. So the first measurement point will give that flow a grade of 0.05. This grade is smaller. This grade is smaller than the grade of the monitored flow with the highest grade, 0.2 in this case. So the measurement point will choose to monitor the new flow instead. And the same happens in the second measurement point, but now the time to live decreases by 1. So the time to live now is 254, which means the target value now is 0.33. So the distance between the target value and the hash value is 0.28. The grade is smaller than the grade of the flow with the highest grade, which is 0.3 in the second entry in this case. So the measurement point will choose to monitor the new flow instead. And also the same happens in the last measurement point. Now the time to live is 253. So the target value is 0.66. The distance between the target and the hash is 0.61. The highest grade, the grade is 0.21. So the grade of the flow is higher than the grade of the largest monitored flow. So the network measurement point will choose not to monitor the new arrival. Now let's see how to calculate the target value. We suggest two approaches to calculate the target value, the greedy approach and the folding approach. Let's start with the greedy approach. We choose a target value for 255, and for the target of 254, we will choose the point that maximizes the minimal distance from the target of 255. The same thing for the target of value of 253. We will choose it to be the point that maximizes the minimal distance from the target of 255 and the target of 254 that we already chose. And also for the target of 252, we'll choose it to be the point that maximizes the minimal distance from the previous 3 points we already chose. If multiple points maximize the distance, we choose only one of them. So for example, we chose the target of time to live 255 to be the 0.01 on the unit circle. So now the target of 254 will be the point that maximizes the minimal distance from 255. In this case, it's 0.5. And now for the target of 253, it will be the point that maximizes the minimal distance from those 2 points. There's 2 points that maximize the minimal distance, 0.25 and 0.75. We will choose one of them. Let's say we chose 0.25. Now for the target of time to live 252, we'll choose it to be the point that maximizes the minimal distance from these 3 points. It is the point 0.75. The greedy approach is not optimal because, for example, if we have a path with 3 measurement points, the target value is not spread uniformly on the unit circle. The target value is not spread uniformly on the unit circle, as you can see. But this approach is simple to implement and works reasonably well. The second approach we are suggesting is the folding approach. The folding approach is exactly like the greedy approach, but the target can be multiple values. So we start, in the start, we chose a value for time to live 255. Then we chose all the points that maximize the minimal distance from the target we chose for 255. And for 200 to be the target of 254. And for 253, we'll choose all the points that maximize the minimal distance from the 2 points we already, the target of 255 and the target of 254. And also for target of the time to live 252, we'll choose it to be the point that points that maximize the minimal distance from the targets we already chose. For example, let's say we chose time to live the target of time to live 255 to be the 0.01 on the unit circle. Now the points that maximize the minimal distance from this point is also the point 0.5. So the target of time to live 254 will be the point 0.5. Now the points that maximize the minimal distance from those 2 targets we chose are the points 0.75 and 0.25. So we'll choose both of them to be the target values of time to live 253. And now for the time to live 252 will be the 4 points that maximize the minimal distance from the targets we already chose. For the time to live 251 will be the 8 points and then the 16 points. And as we can see in this approach, the number of values, the target multiplies by 2 each time the time to live decreases by 1. That's why we will calculate the distance between the target and the hash using the folding approach. Because as we said earlier, the grade is the distance between the target and the hash value. And when we have a target that multiply by 2, the complexity to compute the grade will also multiply by 2. So the folding approach, we will use the folding approach to calculate the distance between the target and the targets, because there's multiple, and the hash. We will take the circle and we will look at it as a plane, the unit circle. When the time to live is 255, we will calculate the distance between the target and the hash directly. The same for time to live 254, we will calculate the distance between the hash and the middle of the plane, and that will be our grade. As we can see, the middle of the plane is 0.5, and that's exactly the point that maximizes the minimum distance from the point 0.1. And for 253, we will fold the plan and calculate the distance between the hash on the folded plan and the middle of the plan. And as we can see, the middle of the plan is the point 0.25 and 0.75, which are exactly the points that maximize the minimal distance from the target, which was for time to live 254 and 255. So we will, the distance will be the distance between the hash on the folded plan and the middle of the plan. And now to calculate the time to live 252, we will fold the plan again and calculate the distance between the hash and the middle again. These are the points that maximize the distance from the previous targets. And so on. Each time we fold the plan and calculate, each time the time to live decreases by 1, we fold the plan and calculate the distance between the hash and the middle of the folded plan. Of course, the hash of flows with the smaller time to live is more likely to be closer to the target from the hash of flows with the higher time to live, because the plan is folded. So naturally, the distance between the points on the plan are closer. So each time we fold the plan, we will scale it back to 1 to enable fair comparison of flows that visit the measurement point with different time to lives. Through initial exploration, we discovered that cooperative flow selection is almost optimal until we reach high flow coverage, about 95%, but ineffective in moving from high coverage to full coverage. As I said earlier, in network-wide measurement, optimality is the highest coverage possibly achievable by any offline algorithm. We will compare our algorithm with the flow radar, a network measurement algorithm. Instead of flow radar, instead of sampling existing monitoring solutions, it aims to provide full visibility to all the flows all the time. In flow radar, each measurement point encodes all the flows that arrive in it in its available memory, and then when the encoded data is sent to the controller decodes the data and recognizes the flows. there's no communication between measurement points in flow radar. We will compare our algorithm with flow radar for a given number of peer switch entries. Each entry in our algorithm has a flow ID, packet count, byte count, and grade, as I said earlier. In flow radar, instead of grade, it has a flow count. Therefore, we estimate that each entry flow radar has a similar size of hours, which makes this a fair comparison. As I said earlier, optimal in highest coverage possibility, optimality is the highest coverage possibly achievable by any offline algorithm. As we can see, our algorithm, our cooperative flow selection in red, we can see it. It's near optimal until reaching a high coverage. It's near optimal, and then here we zoomed on the high coverage area, and we can see that it needs 2 times more memory to reach full coverage after the optimal reaches full coverage. And as we can see also in the graph, the problem of flow radar in black, the problem of flow radar that it's impossible to decode the flows when the memory is too small. So the flow coverage is 0 until there is enough memory, then it makes a sharp ascent to full coverage. We also can see that the folding perform better than the greedy. To solve the limitation of cooperative flow selection, we suggest cooperative flow selection flow radar. We run flow radar and cooperative flow selection in parallel. We assign part of the measurement point memory to a cooperative flow selection and part to flow radar. Flow radar run on the flows that were not captured by cooperative flow selection. And in this way, we took the best of the 2 worlds. As we can see, cooperative flow selection flow radar in cyan, it reaches full coverage with optimally, with the optimal, and also it performs like the flow radar in the high coverage area. And from the start to high coverage, it also performed near optimal. So the new cooperative flow selection flow radar took the best of the 2 worlds. So it's near optimal all the time. And as you can see, the greedy in blue needs a bit more memory to reach full coverage. In conclusion, we saw a way for measurement points to cooperate in order for each measurement point to monitor different flows than the others without communicating between them. We saw that this method achieved a great result until reaching high coverage, and by combining it with the flow radar, that also doesn't require communication between the measurement point, it achieved a great result, also from high coverage to full coverage. Thank you for listening to my talk. I'd be happy to answer any questions.
Thank you very much, Bilal, for your interesting talk. Are there any questions out there?
Since the talk is too complex, really we can't understand very well, but it's super. We need to read the paper. Thank you.
Thank you. Thank you for listening.
Are there any questions? Are there any questions? I have quick question. So, Bilal, how do you capture or simulate the optimal results?
The optimal, we assume that all the measurement points can communicate, and they know the flows, the path of all the flows, and they arrange between each other what flow to monitor in order to monitor all the flows. So basically, we did each time a flow travels through a path, the measurement points will communicate. The measurement points already know all the flows, the paths of all the flows, and then decide which of them should monitor this flow.
Okay, so based on prior knowledge, you assume that this result, this particular.
Exactly, and that's the highest performance that any algorithm can achieve.
Have you sort of have you thought of proving that using any optimization framework, or?
Sorry again.
Have you thought of proving that optimality using any optimization framework, or? I
didn't understand. Sorry.
So what I'm saying is that you based on the prior knowledge, you assume that this particular selection or this is the optimal result. But have you thought of proving that one using any optimization framework, proving the optimality of that result?
Yeah, it's in the paper. We proved that the measurement we did, our implementation for optimal algorithm is actually the optimal the highest that can be achieved.
Yep. Thanks. Are there any other questions out there? No questions. Can I ask you another small question? Yeah. So you basically propose this you use greedy and folding approach, and from the results we can see that there's a not like significant improvement in folding approach compared to greedy algorithm. So what do you think in terms of computational complexity? Have you checked the computational complexity of using both type of algorithm?
We didn't actually did a comparison with complexity, but we saw that, and it's obvious that the greed algorithm is optimal, and in greed algorithm we can calculate the targets in priority. So to make a cache that each bit time to live, what's the target, and we can prepare, and it's even simpler. And the thing is, it's right that they are not perform very different, but as we can see here, that a little different. Make that the folding reached full coverage before the greedy did. It needs square 2 more memory to reach full coverage.
Yeah, I understand. Yep. Thank you.
Right.
All right. One last time, are there any other questions out there? All right. So if there's no more questions, let's thank the speaker again. Thank you, Bilal. And let's move on to our next talk. Our last but not least presenter is Zhijun Wang from University of Texas at Arlington. Let's welcome Zhijun to present their paper titled HOLNET, a holistic traffic control framework for data center networks. Are you ready, Zhijun?
Sorry,
Can you
see my,
yeah, can you hear us?
hello?
Yep, we can hear you.
Okay. Can you see my slides, share slides?
Yep.
Okay. So, hello everyone. My name is Zhijun Wang. I present framework for data center networks. So there are many traffic control protocols have been proposed for data center networks. This table and the table in the next slides show the most existing traffic control protocols. From the table, we can see most of those protocols are point solutions. For example, from here, we can see all those protocols are focused on the congestion control, include the single parts or multi-parts. And the other traffic control protocols, they are focused on the in-network load balancing. However, a point solution, they have to coexist with the other point solutions. And this may result in suboptimal or unexpected performance or even network instability. And the second problem for the existing traffic control protocols is the most existing protocols are designed empirically. So they lack the theoretical foundation. So their convergence, stability, and optimality are not proved. Although some optimal solutions has been proposed, those protocols are majorly based on the network utility maximization, or we call it the NUM method. So for a NUM method is inactive flows share bandwidth link. So the NUM solution is to maximum the weighted user utility subject to the bandwidth constraint. So the traditional NUM is a symbol to maximum the overall social welfare without fairness criteria. So a user utility function is the first order of the quality of experience to determine the degree of user satisfaction. So yearly, a user utility value can be defined between 0 and 1. The value 0 means the user is fully unsatisfied, and the utility value 1 means the user is fully satisfied. As Shank pointed out, there are typically 4 types of different user utility functions for internet. So include the utility function for long real-time elastic service and real-time rate adaptive service and the real-time delay adaptive service and hard real-time service. So this figure shows that those 4 typical user utility functions. From here, we can see the non-real-time elastic service. They usually have no minimum rate requirement, but for the real-time services, they usually need a minimum rate guarantee. So when the rate is below this minimum rate, then their utility will quickly drop to 0. However, the traditional NUM solution they cannot provide the minimum rate guarantee. And another problem for the long solution is it is hard to deal with more than one different user utility functions, or even a single user utility, but with different saturated rates. It's also hard to handle. A saturated rate we can define as the maximum, the rate that maximum the user utility. For example, for the video flow and audio flow. So the saturated rate can be defined as the highest video or audio encode rate. And for the non-real-time elastic service, the saturated rate can be defined as the maximum link rate. Now let's look at one example. For example, we have a video flow and audio flow that share a link. And the saturated rate for the video flow is 1 megabits per second. And for the audio flow is 200 megabits per second. And they also have the minimum rate requirement for the video flow and audio flow are 250 kilobits per second. So if both flows have the same utility function, the share and link, then the traditional line will equally allocate the bandwidth to those two flows. However, in this case, for example, they share 280 kilobits per second link. So the audio flow can reach their minimum rate, but the video flow cannot. So as the most existing traffic control protocols in the data center network are point design and empirically point solution and empirical design. So it is necessary to develop a principled and a systematic framework. So this framework should allow fully integrated congestion control and in-network load balancing protocols to be developed. And also all the protocols under this framework, they should have probable convergence, stability, and optimality by design. So to achieve this objective, we propose HOLNET. So HOLNET is based on a new network utility maximization method we call HOLNET norm. So HOLNET norm can provide a minimum rate guarantee and deal with different user utility functions. Now we discuss how the HOLNET norm can provide the minimum rate guarantee and deal with different user utility functions. So the traditional norm is to maximum the weighted user utility subject to bandwidth constraint. In the HOLNET norm, we add another boundary condition. That is, we add the minimum flow rate constraint as a boundary condition. So in the HOLNET norm, so is to maximum the weighted user utility subject to bandwidth constraint and the flow rate constraint. So this is the HOLNET norm to provide the minimum rate guarantee. I set the minimum flow rate as a constraint into the optimization problem. Now we discuss how HOLNET norm deal with different user utilities. So the HOLNET norm provide a central utility file list. Then we introduce a new concept we called central utility rate. So this concept is borrowed from the center of mass in physics. A center of mass is a point of an object. At this point, the mass is balanced. For example, we have an uneven bar. So the center of mass is a point. At this point, the mass is balanced on the both sides. So this we call the center of mass. So similarly, we can define the derived rate of the user utility related to the rate as the mass density, then we can define the central utility rate. So the central utility rate is the rate which balances the utility. So based on the central utility rate, we propose central utility fairness. The central utility fairness is if two flows I and J they share link, so the rate allocation for those two flows is proportional to their central utility rate. So this is the central utility fairness. Now we discuss how the HOLNET handles different user utilities. So in the HOLNET LAM, we first select a base utility function, UCX, and with a base central utility rate, XC0. And we can set the weight for this base utility to be 1. For whenever a new flow with a function, utility function, UIX, and a central utility rate join into the system, then we convert this utility into the base utility with a weight omega I. So the omega I is computed based on the base utility and the utility of flow I and their central utility rate based on the central utility fairness. Then this utility function is mapped to the base utility function UCX with a weight omega I, subject to bandwidth constraint and the flow rate constraint. So in the HOLNET LAM method, so it first allocate the rate, the minimum rate to each flow to try to guarantee the minimum rate, and then they allocate the actual flows rate based on the central utility fairness. Now we use one example to discuss what the difference for rate allocation between the HOLNET LAM and the traditional LAM method. So use this same example as we stated before. So we suppose the central utility rate for those two flows are 500 kilobits per second and 100 kilobits per second for the video flow and audio flow. So their central utility fairness rate allocation ratio should be 5:1. So if those two flows share a 208 kilobits per second link, so the traditional flow, the traditional LAN solution, so the rate are equally allocated. So each flow will get 140 kilobits per second. But in the HOLNET LAM solution, so the first, the minimum rate of each flow is allocated. So the audio flow first get the 50 kilobits per second rate, and the video flow will get 200 kilobits per second rate. So the actual 30 kilobits per second flow rate we allocate to video flow, so they can approach to the 5:1 ratio. So from this example, we can see the HOLNET LAM. So the first can try to meet to provide the minimum rate guarantee, and then try to allocate the rate based on the central utility fairness. So we skip the mathematical formulations for how to derive the congestion control rule and the in-network load balancing control rule. Now we are discuss the design space under the HOLNET. So after we select a base utility function, then a family of congestion control protocols can be designed based on the capability of the core network. So if the core network cannot provide any feedback, we can consider the core network as a black box. Then we can design distributed end-to-end congestion controls protocols like TCP. So we can, under the HOLNET, we can design the elastic congestion control, we call it CC, single part or multi-parts. And also we can enable the minimum rate guaranteed service, so we can provide multi-class of services, we call it single part or multi-parts. So those are similar to the TCP protocol. They don't need any feedback from the core network. So if the core network is available to provide hub-by-hub feedback, then we can design integrated congestion control with in-network load balancing. So we can design a congestion control combined with the load balancing, single part or multi-parts. And also we can enable the minimum rate, so we can provide multi-class of service, single parts or multi-parts. So therefore, those 4 types based on if the core network can provide hub-by-hub feedback. So feedback information in the HOLNET is only a binary information. That is, we only needed to know the next hop is congested or not. Now we use some case study to show the flexibility of the HOLNET. Simple cases to show the flexibility of HOLNET. So the first one, we use this very simple topology to design a congestion control with or without multi-class of service. So the first case, we consider the same utility function, but different saturated rate. The second one, we consider 2 different utility functions and one with minimum rate requirement. So this is the result, show the overall utility, normalized utility. So we can see the simulation results is close match to the optimal one in 2 cases. And this is the rate allocation for the case 1 and the case 2. And we also can see the simulated rate is close match to the optimal one. The third case is a multi-pass congestion control protocol. So we use this topology to test the multi-pass flow. One subpath of one multi-pass flow share with a single TCP flow. So this is a rate allocation for multi-path and single path flows. So they are close matched to the optimal rate. And this is compared to the MPTCP. So there are similar results here. So finally, we designed an integrated traffic congestion control and in-node balancing protocol we called HOLNET UTL. That is a HOLNET traffic controller with utility of a TCP-based flow rate allocation. So we choose the TCP utility function as the base utility. So this is a TCP-friendly design. So we test this HOLNET UTL in a 6x6 data center network. So we allow that each core network can provide the better information to its upstream nodes. So we compare with the HOLNET UTL with DCTCP plus the in-network load balancing ECMP and the DCTCP with in-network load balancing Zhou. And we use the web search and data mining workload to test the performance. So we use the flow completion time, the overall for small flow, overall flow, and the huge flow completion time, and the Latin lines percentile. So this is sure the performance compare with the DCTCP plus ECMP and the DCTCP plus GIL. So we can see HOLNET ETI can provide more than 30% gain compared with ECMP and GIL. So they can only a little bit worse performance for small flows, FCT. So in this paper, we propose a new traffic control framework called HOLNET. HOLNET allow integrate congestion control and in-network load balancing protocols to be developed. So the HOLNET is based on the new network utility maximization method we call HOLNET LAN. So HOLNET LAN can provide minimum rate guarantee and also provide essential utility files. Okay, thank you. And the questions.
Thank you, Zhijun, for your interesting talk.
Yeah.
Are there any questions? No questions? Everyone is a little bit shy. No question for Zhijun?
Yes.
All right. I have a small question. So you evaluate the performance under different network loading. Is a load percentage. How do you calculate the load percentage, or what's the network load that you considered here?
Or how you mean how to calculate the load?
Yeah.
That is to calculate this, we have a workload. So for the flow arrival rate, so we can calculate the average flow size, and then we can control the flow arrival rate. Then we can calculate the load percentage.
Yeah. Okay. The other question, so you calculate the optimal value.
The optimal value.
Yep.
Means
So the optimal.
For this case.
Yep.
Yes.
Yep, that's right.
Yeah.
How do you? Yeah.
You mean how to get this optimal one?
Yeah.
This is based on the utility maximization. So we have a utility function for each flow, and based on the topology. So to maximum the utility value, then we can get what the flow rate for each flow. Then we can calculate value. So this is based on the to maximum the summation of the user utility. Then we can get the optimal flow rate, and then we can calculate the optimal user utility.
All right, thank you.
Okay, thank you.
Are there any other questions out there? No questions?
Okay, thank you.
All right, so if there's no more question, let's thank the speaker again. Yep. So I think this brings us to the end of this session. I would like to thank all the speakers again for their interesting talks, and thank you all for joining the session. Bye.